Okay. Okay, I guess today we're gonna kind of review the radiation section following that FE textbook or mechanical review manual. And what I was thinking, I was talking earlier, is that we're gonna go through the main really important topics in radiation very quickly and do some examples along the way. And probably next session would be just more example on what we'll see really radiation on this stuff. So probably 1/3 of the question on heat transfer coming from radiation. 1/3 from conduction, 1/3 from convection. Comment? No? Good? Okay. So, of course, I'm not going to go through the basics of radiation at this point, since assuming everybody kind of we covered it. Even for those who having a current heat transfer, we covered like good portion in the first chapter, right? So if you're going to start with radiation conservation law. You're saying that alpha plus rho plus ha is equal to 1. And if you remember, if you have a plate like this, for any incoming radiation, a portion of this will be absorbed, which that portion is represented by absorptivity that we kind of show it with alpha. The portion, so this is kind of alpha. The portion will be reflected going back. So reflected, which we show it with reflection or rho, and a portion will be transmitted through it. Which we show it with ta. So transmission or transmittivity. Transmissivity for some reason. So this is time, and the summation should be 1, right? So if this is incoming energy, a portion will be reflected, a portion will be absorbed, and a portion will be transmitted. And by the way, the summation is total is 1. Now, if there's example like this.
What is the other squiggly line represent?
Which one? The top?
The one that's pointing down at the top.
The top one is incoming energy, or you can call it G. So the total radiation coming in, is that what you're saying?
Yes.
So the total irradiation to your surface, it can be reflected, absorbed, or transmitted, nothing else. So if we do a quick example on this, which is a part of the kind of question as well, if the absorptivity of a body is 45%, let me say 48%, so consistent with this, and reflectivity is 36%. What's transmissivity? emissivity, which simply what we're saying is that alpha plus rho plus phi is equal 1. Absorptivity is 48% or 0.48. In reflectivity or rho is 36%. And we're looking for transmission coefficient. So tau would be 0.16 or 16 per second. So that's easy. And we also have a body, and we have an opaque body, if you remember the definition. Can I go to the next slide? Okay. For opaque body, what you're saying is that all the incoming energy is either absorbed or reflected. So nothing can be transmitted through the plate. And of course, I have another example here, but that probably is simple. But let's quickly cover it. Example, for an opaque body, as soon as you hear the opaque body, you know that the tau is 0. If 62% of the incident energy which is the incoming energy, is reflected, what is mostly the percent of energy absorbed? Which really following the same relation, you know that alpha plus rho should be 1 for opaque bodies. Rho is 62%, so rho is 62, so alpha is 1 minus 0.62, which is 38, which is 0.38 or 38%. That's your absorption rate.
These wouldn't be examples of what would be on there, would it?
Yes, no, it will be.
That easy.
Exactly.
This is hard.
If this is the hardest thing on there, I would.
No, this is not the hardest one. This show up, yeah. Because you have a good range of questions from easy to difficult. So.
And you can like control F opaque body and you pull that equation.
Exactly. But this one, I mean, probably you know it, right?
Yeah.
Now let's talk about black body, real body, and gray bodies. I don't know what is real body, but we typically cover black body and gray bodies. So black bodies, black and let's say gray bodies. Anyone remember what was black body?
Stove.
Wow, what's the definition? Not example. Anyone? So in definition, black bodies or ideal bodies in terms of radiation and absorption. So if you have a black body, the epsilon, which is emissivity, we didn't talk yet, is 1. But we kind of said in classes that there is no black body. Usually, you can't emit maximum of your power. Looks like an ideal case. So black body is an ideal surface. But gray bodies are the bodies that you can assume emissivity is equal to absorptivity, which we don't talk about, which is the more typical cases. That's what we see. So we use black bodies to kind of finding maximum, theoretical maximum, or something like Carnot cycle. So in definition, black bodies radiate as an ideal radiator. Which means a black body emits the maximum possible radiation. And also absorbs all incident energy. So looks like, imagine it's in a hot summer, you are in Miami, Florida perhaps, and you're wearing a black shirt. So you are kind of absorbing maximum incoming solar radiation. So that's not a black body, but kind of you can relate it to that black shirt you have. So with black body, you emit maximum and you absorb maximum as well. So another definition for black body that I can't find it here is that epsilon is 1, or emissivity is 1. Emissivity, that's the ability of the surface to emit the energy, is maximum. And absorption, or absorptivity, is 1 as well. So that's what we get out of those definitions. Really, we can do it in our calculation. Epsilon is 1, alpha is 1 for black body. Now that we have some definition, let's use one equation to calculate radiant heat transfer. So to find the rate of heat transfer by radiation, or Q dot. So here, Q stands for energy, and dot takes care of the rate of energy. It's rate of energy, or energy per second, Q dot, is equal to emissivity of the surface. If it's a black body, it's 1. If it's a gray body, it's somewhere between 0 to 1. By the way, if I go back, we didn't talk about gray body really. because here we didn't talk about gray body, but for gray body, if I talk about it here, gray body is real body. It's not ideal case, is what we have here, for example. If for whatever incident energy we have on this board, a portion will be reflected, a portion will be absorbed, right? So for gray body, epsilon is equal or greater than 0 and less than 1, and if it's 1, it's black body. And by the way, epsilon and alpha is assumed the same in gray body. So if you have a gray body with the epsilon of 0.5, you can assume the alpha absorptivity is 0.5. So that's how we work with gray body. Now going back to this radiation heat transfer equation, Q dot, the rate of heat transfer is epsilon, the emissivity, times sigma, which is the Stefan-Boltzmann coefficient, it's a constant number, times the area of the surface. Then you're going to find the rate of heat transfer from that surface, times its temperature in absolute value, which is Kelvin in SI, to the power of 4. And I typically suggest to remember the Stefan-Boltzmann coefficient value.
Is that a sigma?
This is, yeah, lowercase Stefan-Boltzmann coefficient. And sigma is 5, 6, 7, 8, or 5.67 times 10 to the power of -8. And the unit for this is watt per meter square times Kelvin to the power of 4. So a quick example on this. Yeah, 17 meter square plate with an emissivity of 0.26 is suspended vertically in a large room if the absolute temperature is 430 Kelvin, what is most nearly the radiation emitted? What is the radiation emitted? So we know the surface temperature in Kelvin, that's if it's not, we should add 273 to C to make it Kelvin. And we know the area, we know the emissivity, and the Stefan-Boltzmann is a constant number. So to find the radiation emitted, simply I'm going to use the equation I have here. So Q dot is epsilon A sigma temperature to the power of 4, which is 0.26, area 17, sigma 5.67 times 10 to -8 watt per meter square of 4, and temperature is 430 to the power of 4. So the Q dot in this case is 8.6 kilowatt.
So the radiation part seems like it won't be too bad. So far.
No, it gets bad.
Don't say that.
So when we get into enclosure, that's really the hard question coming. But this is the basic, and those are important too. Those will be part of the question. Can I go to the next slide? I got it. So a quick review is for black body. We said alpha equal epsilon equal 1. For gray body, alpha equal epsilon, and alpha is between 0 and 1, and epsilon is between 0 and 1. And we also said for opaque body or surface, for opaque gray body, we have epsilon plus rho equal to 1. Now for my current heat transfer, students, is it difficult or are you guys following? I have another simple example. Do you want me to quickly show it as well? This is really short as well. Example. If 55% of energy, by the way, if you can solve it quicker than me before I start solving this, just tell us the answer. If 55% of energy from a gray body supposed to be body is reflected, what is the emissivity of the body?
Is this for an opaque gray body?
Say it again.
Is this for an opaque gray body or just regular?
It says if 55% of energy from a gray body. That's right. 45. So what we're saying is that so what we said for a gray body is that epsilon, did we say epsilon? Yeah. So for gray body we said epsilon and alpha are the same. And now here is asking about emissivity, which is epsilon. So if you find alpha, that's the answer already. So what we can say is that epsilon plus rho equal to 1. Remember that for an opaque body, we didn't say opaque, right?
No, we didn't. That's why I would
That's
thought it
what
wouldn't
it is,
be.
Yeah, the question doesn't bring OPEC, but you can say, yeah, I would add OPEC just to make sure it's not approximate information from gray OPEC button. So what happened is that from the incident energy, let's say incoming energy GI, a portion will be reflected, a portion will be absorbed, right? Nothing can be transmitted. So if I don't follow this book manual, I would say rho plus alpha is 1 because we're dealing with OPEC. And since it's gray body, alpha is epsilon. So rho plus epsilon is 1 since it's gray body. And we already know 55% is reflected. So if rho is 55%, then epsilon or emissivity is the remaining 45%. So, question on this?
If that wasn't okay, would you just add a 45%?
So if that was not opaque, I would say, not by 2, but I would say some part of this could be transmitted. So here I would add tau as well. And then this, so epsilon plus tau would be 45%. And then somehow we should figure out what was the transmissivity. Not divided by 2, but that would make it totally different. But this, since this is opaque, no radiation can transmit, so it makes this simpler in this case.
So if it wasn't opaque and we didn't have tau, we wouldn't be able to solve it.
Yes, and if there were no input information, I would just simply, let's assume transmissivity is equal to this, which is a just out of air assumption, but that's better than. So again, for those multiple choice, it's tricky, but if it's a kind of final exam, you could say assuming tau is 0, assuming tau is 0.5, you could do something. But for multiple choice, for this case, I would go ahead and assume it's opaque and do it. Now, starting now that I'm going to talk about view factor and get it into exchange of energy between two surfaces, it's the more difficult part of it, which is not difficult, but the more challenging part. So let's talk about view factor or shape factor, some people call it. So view or shape factor. Based on the definition, the view factor which we show it with F sub I J, Fij, is defined as the fraction of radiation leaving surface I that is intercepted by surface J. So Fij. So you can assume we have surface I like this. This is surface I, and we have surface J like this. Now, radiation from surface I can go any direction, right? You can't limit it to go only this way. It can go this way, all different directions. So the portion of the surface I radiation that is intercepted by surface J, that's the view factor. If I'm gonna pick another color and show other radiation that we don't care because they're not intercepted by J, you can see this a lot, right? So the portion that is only intercepted by surface J is a view factor. So view factor maximum is 1. If 100% of surface I is absorbed by surface J, then that's a maximum 1, but anything else is less than 1. And in heat transfer on this section, we go to really different scenarios to find what's the Fij for this configuration. This probably don't talk about it here much, but
You know, like I'm just making sure that this isn't, you didn't draw this for this reason, but that line, does it have to be perpendicular?
no. So for example, this will be part of Fij2. So whatever radiation from I can be seen by J from the J. So there are two view factor relations that we're mostly using these two to come up with the view factor value. View factor relation. One is that, which is we call it reciprocity relation, is that area of surface I times Fij is equal to area of surface J times Fji. So if you work with the location of I and J where which one comes first, and change the value, right? Fij is totally different than Fji. So if you know Fij and you know the surface areas, you can find out Fji. So that's called reciprocity rule. Relation. And second relation, this is 1. 2 is summation of Fij, J from 1 all the way to N, and is the maximum number of surfaces in an enclosure, should be 1. We call this summation rule. Which I can explain this more here. If you have enclosure like this, let's make it really small. So let's say this is surface 1, this is surface 2, this is surface 3, and this is surface 4. Okay? Here, if I'm going to show the summation rule inside this enclosure, is that I can say summation of F1J j from 1 to 4 because I have 4 surfaces, including 1, should be 1, which means that f11, nothing but the view factor or the portion of the radiation leaving surface 1 and absorbed by surface 1. And believe it or not, for some surfaces like this, a portion of this will be absorbed by itself. In some flat surfaces, F11 is 0, but depends on the case. And F12, so I'm just keep adding J12, which is F12 is the radiation of surface 1, which is absorbed by surface 2, which you have, of course, a lot. F13 plus F14, the total should be 1. That's what we're saying.
So that's an enclosure.
This is enclosure. This is a rule for enclosure. And N is the different dimensions you have inside one enclosure. By any 2 surfaces, you can make an enclosure. Probably I can show it here. But by any 2 surfaces, for example, if you have a surface like this, probably like this is surface 1, and this is surface 2, now you have an enclosure. Is F11 make sense? A portion of radiation leaving that surface which is absorbed by that surface. So that's view factor. And
If you had like a 3-dimensional box with sides 1, 2, and 3, nothing gets missed out the top because it's perpendicular.
say that again, if you have a 3D box, so
As in, instead of just 4 lines there, you have 4 boxes that are facing each other. The same scenario.
still should work. Really, let's see. So are we talking about something like this?
Yes.
So now you have more surfaces. But it's still, it's an enclosure, it will work. Absolutely. In reality, we don't have a 2D enclosure. There's always a thickness. And we'll do examples really later. Even we have it in this textbook that inside an oven, cooking oven, you can really use this relation. So it definitely works. Now, we are using view factor to somehow find the exchange rate between 2 or more surfaces. So in the previous equation, which was here, this is just the amount of radiation from one surface. We only have one temperature point, right? T is, like in this example, was 430 Kelvin. Now, what if that we have this wall hot, like a side of the oven, and the other side inside this room, which is enclosure, is cold, or other sides are cold. And what's the exchange rate between this hot wall and that particular wall? Now that's where we need view factor. So if I'm gonna talk about before that, let me, did I say Fij is, I guess I said, but I didn't write it down. So just a quick reminder that Fij maximum is 1 and minimum is 0. Fij is between 0 and 1. If you want me to do more examples on Fij, I can quickly open the textbook, talk about it more. But let's move on, and but it's up to you. If you want me, I can talk about different things. But as soon as we do 1 or 2 examples, you exactly know what we're talking about. So let's talk about the net radiation. Heat transfer.
So those are the only two view vector relations that we're talking about.
That's only two. Reciprocity rule, A1 F12 is equal to A2 F21, and summation of all U factors inside an enclosure should be 1. F11, F12, F13, F14, F15, add them all together should be . So net radiation is, you're saying that when two bodies can see each other, if they have eyes, perhaps, then each will radiate energy 2 and absorb energy from the other. So the net rate of heat transfer between the two bodies can be calculated using this. So Q dot of 1, 2, or let me show this, 1, 2 equal to. So let's say we have surface 1 and we have surface 2, right? Now surface 1 has a temperature T1, surface 2 has temperature T2, the net rate between 1 and 2 is equal to the Stefan-Boltzmann coefficient, which is a constant number, sigma, times area of surface 1 times view factor of 1, 2 times temperature of 1 in absolute value, not in C, in Kelvin, to the power of 4 minus temperature of surface 2 to the power of 4.
No acidity.
No acidity because we're assuming it's the black body. But let's see. Yeah, the next one has emissivity, which really is not the case. Now, if I'm gonna write it in the form of using A2, I would write it this way: that this is equal to same value is sigma. Instead of A1, I'm gonna put A2. Instead of U factor F12, what should I put? F21. Because reciprocity rule 1 was that A1 F12 is equal to A2 F21, right? And everything else is the same. And in some cases, you need to do this because you know F21 and you know the area values, so you have to write it in this form because otherwise you have to calculate. So F12 is a shape factor or configuration factor, which depends on shape, emissivities, and orientation. Sigma epsilon. So in more general case, you have to put epsilon as well, which we call it for a small body. So let me follow this format as well and say, so should we kind of have a list as well? Unrotated, name, probably email to in case. Just keep it as a record. So let me complete this. Based on this, the net radiation heat transfer for a small body is epsilon sigma A so okay, let me write it down. Epsilon sigma A T1 to the power of 4 minus T2 to the power of 4. And if I'm going to talk more about that, a small body, based on this, it says if body 1, the first surface, is small and completely enclosed by body 2. So what would be the view factor of F1, 2 if body 1 is completely enclosed by body 2? F1, 2 is 1. So we're talking about this. If body 1 is, if this is 1, or yeah, let's put it this way. Yeah. So imagine you have a donut shape enclosure, and the inner circle is 1, the outer circle is 2. So the surface 1 is totally enclosed by surface 2, right? So F1 to 2 is absolutely 1. Because no radiation from 1 can go back to itself. It doesn't go through the curve, right? So everything should go to 1. So here it says if body 1 is small and completely enclosed by body 2, then F12 is equal to epsilon 1. So really, this is not what we say here in the textbook we teach. Or that's kind of unique to me as well. So, but that sounds right. If this is the case, looks like you can rewrite this into this one. Probably that's a kind of test hint or whatever it is. Now let's do an example on this. I go to next. So example. An ideal radiator is maintained. So when you have an ideal radiator, that means it's a black body, epsilon is 1, alpha is 1, right? An ideal radiator is maintained at 550K. It is enclosed in a tank with a temperature of 290K. The radiator is small compared to the radiator is small compared to the tank. So that should trigger that second equation. This is a small radiator. What is most nearly the, or I would say find the net heat transfer between them per unit area of radiator. Per unit area of radiator. So we know that epsilon is 1 because we're talking about ideal radiator. And we're going to use the Q.12 of epsilon sigma A T14 minus T24. If I go one slide back, that's this equation, right, we talked about. If you have a small body, based on the definition we have two surfaces, and one of them is a small compared to other. We're going to find the net radiation between. But we're talking about per unit area of radiator, so I would simply divide it by area. So divided by this A, I have epsilon sigma T14 minus T24.
T1 is the radiator, and T2
T1 is radiator, or the hotter one. And when we're talking about the net rate, you want to bring the larger one first, so you make it positive. Otherwise, we just talk about the direction. So epsilon is 1 because ideal surface. Sigma is always 5.67 times 10 to negative 8. T1 is, both of them are in Kelvin already, so 550 to the power of 4 minus 290 to the power of 4. And if you know the answer, is 4.8 kilowatt per meter square.
So the fact that it says that it's an ideal radiator doesn't matter.
Yeah, it's ideal radiator, that's why we got epsilon equal to 1.
But then it says it's small, so we use the.
So when it says it's small, we can use this relation.
Which would have been the same as using the other one, right? Since it's going to be 1.
But the other one, we had a view factor. See? But it's still, for this case, so the other one, it had a view factor, which in this equation we don't. But it's still, if you look at it here, it says the radiator is a small. No, sorry. It is enclosed in a tank with a. So it didn't say it's fully enclosed or something like that. So you can have. If this is your surface 1, and this is your surface 2, still surface 1 is enclosed by surface 2, but some part of the surface 1 goes back to surface 1. So you have a view factor here. But when it says a small, the good thing is that if you get rid of view factor, you can use this relation.
Does it have to explicitly state that it's small, or is there a calculation to determine that it's small?
No, that's kind of similar to gray body or black body. When in radiation you hear that one surface is small compared to other, that will kind of simplify some of the equations.
So
We don't quantify this really.
it doesn't specify otherwise, could you just assume that it's small?
No, the question should tell you this is small, and that's why based on that compare. But if you're asking about what ratio we're talking about is small, I don't know, or we don't specify that.
And so if it doesn't say that it's fully enclosed, then you just assume it's not fully enclosed. Like if it just says enclosed.
Exactly. If it says enclosed, I would say it might be fully, it might not be fully. So you don't know. You need more information. Now, next section, which probably I don't go there, is about next the net radiation heat transfer with black bodies. That which is some example. Now, do you want me to continue, or let's just start with this one, 6 to 7 kind of thing, and we catch up next time. So, really, next session, probably with half of the session, we can complete this, and remaining we just do example by example.
Someone said something about we could get that formula sheet for free. Did like
Yes.
get that, or did we get that?